Let's look at this question. So a digital audio system used the oversampling technique to relax the requirements for the anti-imaging filter. Okay, that means if you want to use a lower order filter, you can oversample your signal. We're going to see how this works and why. Okay, and overall specification for the system are as follows. So that's the useful signal, 0 to 250. That's the signal we want to, the frequency components we want to keep, and input sampling frequency is 1 kilohertz. Output sampling kilohertz is 9 kilohertz. So in total, the M equal to 9. Okay, and stop band attenuation, this time we got a dB here. Okay, pass band ripple is 0.5 dB. Design a two-stage interpolation system. So M1 equal to 3 and M2 also equal to 3. 3 by 3 is 9. Okay, for each interpolation filter, indicates the pass band and stop edge frequency. Okay, we need a low pass filter to do that, and number of filter coefficient for each filter. Okay, so basically we want to have to find out the N for each filter. So in system level is we have 1 kilohertz signal goes in, and we have a 3-time oversample, and the signal becomes 3K, and we need a low pass filter number 1. Okay, we need an anti-image filter, and after that is still 3K, and we need another 3-time upsampling and low pass filter number 2. Okay, and this one it become 9K, and this is 9K as well. Okay, so this is the whole process. We're gonna design these two filter, right? Okay, so let's see what happens. Okay, if we have a time series like this, okay, and initially we have a, let's see here, 1 kilohertz signal, all right, for the Nyquist frequency. It will, fold at 500, right? And 250 is the 250 is the frequency which is we care about. Okay, 250. That's the frequency we really care about. Okay, so you can have a filter that. So let's see. You have this one. Okay, you have a filter look like this, and what happened is gonna fold like this. Okay, so that's the original signal. It may look like. Okay, and things you this is 2. So since you upsample it 3 times, so the signal will repeat itself 3 times. Okay, this is what we call imaging. It's always actually repeat itself, but before you upsample it, you won't see it. Okay, so all right, so not that much, so it's up until here. Okay, up until here. So these mirror or image always exist, but if you don't sample that frequency, you won't see them. Okay, for this one, you only see up to 3K. That's what you see. Okay, and you can see that all these are images. Okay, all these are images which we don't really want. Okay, oops, up until here. So all the image up until here. That's the image. Okay, you can design a filter look like this red one, or you can design a filter like a cut at any frequency, maybe not a 500, maybe 400 or 300, whatever. But if you have a sharper transition, you will have a higher order n, which is come with a cost. Okay, but you need to have a filter at least at cutoff at this frequency. You can't have 600 frequency. You can't not, because this will cause anti-aliasing problem. Okay, there will be overlap here. All right, so for the first stage, so low pass filter number 1, then we need to design a low pass filter look like this. So this is 250 and this is 500. Okay, if we know that, we can start to use those equations to find n. Okay, so where we start, let's find this delta p and delta s. Okay, for S stop band attenuation 50 dB, we got the equation like this. So the delta S equals to negative 50 dB. Okay, although it says 50 because it's attenuation, so it's negative 50. So it's actually equals to 20 log 10 delta p, delta s, sorry, delta s. So the attenuation, so we'll say that. So the attenuation is the attenuation. Attenuation is negative 50 dB, and we want to have this ripple delta s. Okay, so if you do that, the inverse part of that, so you will get this delta s equals to 0.00316. Okay, and delta p, we got that this is a delta s in dB form. Okay, so the delta s in dB form. Then we have this delta p in dB form, which is 0.5 dB equals to 20 log to the base of 10, 1 plus delta p. Then you will find that delta p equals to around 0.059, and because there will be two filter, okay, and this pass band attenuation will split into two, so the delta p hat gonna equals to 0.059 divided by 2, so this is around 0.03. Okay, that's the delta. So we know this. Sorry, we know this. The delta f, the normalized one, equals to the frequency difference 500 minus 250 and divided by the frequency here, 3K. Okay, the frequency after this interpolation. So this one gives us 0.0833. Okay, and if we add everything here into that, you got n equals to 24. Okay, you can plug in everything. You will find this is 24. Okay, then what's next? All right, probably I need move this one a little bit. So when we upgrade it again, okay, so in this case we applied a filter. Okay, we applied a filter and cut off at 500. So these will be gone. Okay, these will be gone. All right, what we got is this. Then it's been updated. It's been upsampled 3 times again. Okay, so instead of this 3K, then we have something, 6K. Okay, and we go something like 9K. Okay, so these will be repeat. All right, so this will be repeat, and this will be repeat, and this will be repeat. This will be repeat. Okay, and what those critical frequency is. So for this one is 500. This is 3000 minus 500. All right, that's the frequency, 2.5K. Okay, and what about this one? This is 3.5K. What about this? Is 5.5K. Okay, and this is 6.5K, and this is 8.5K. These are the critical points. So now, what about the new filter you want? Okay, again, you want the passing band. You want your passing band still be 250. That's no problem. And you want your stop band. Of course, you still can have this little filter like this. You will cut off everything in between, but you will require higher order, like 20. How much was that? 24, right? We did it. So because there's nothing in here, so we can actually put our stop band all the way to here. Okay, make it really relaxed. So in this case, we can have a lower order, much lower order filter. Okay, so let me write like this. So the low pass filter number 2, what we required is a long one. So the passing band here is 250, but the stop band can be 2.5K. All right, so a filter like this, that's the filter. All right, so in this case, we know the stop band attenuation, check. We know the passing band hat, check. Then the delta F here is 2500 minus 2.5K minus 250 divided by 9K. Okay, because after interpolation we got a 9K. So this one 0.25, and if you plug everything into that equation at the beginning, you got N2 equal to 9. Okay, let me shrink a little bit so you see everything. Then we actually try to use this equation to determine the filter, the order of the filter, and you can see that we can relax the stop band for the second one. If we have this filter, we can successfully eliminate these image. Okay, eliminate the image, so keep that one left. All right, so where's that one? That's the final filtered signal which we got here. Okay, in this point we got a clean signal look like this. All right, cool.